Well, welcome back. I hope you've all filled up enough that now you'll be ready to hopefully not fall asleep. Hope I don't fall asleep. So we've talked about Poisson regression so far with respect to explanatory variables that are continuous. Now we're going to talk about, as Chris did earlier with logistic regression, we're going to talk about what happens when you have categorical explanatory variables in a Poisson regression. And the way we handle that is, this is why Chris spent so much time being careful. That way I get to spend so much time, or so little time not being careful. I get to just say, well, we just do the same thing again. I'll show you a little bit about how this works, but not in as much detail as Chris did. So if we have a categorical variable x, and suppose that has capital I levels, then as we did with logistic regression, we'll create I-1 indicator variables. And as Chris did, we're going to label them starting from x2 rather than x1 because of the fact that R automatically drops out the first level and starts assigning categorical variables, starts assigning indicator variables to the second, third, and fourth all the way to the end. So we decided that we would number our variables accordingly. So we have variables x2 through xi representing the indicator variables. And then we will have a log linear model that's just exactly the same as what Chris showed earlier, except that now we're using the log of mu instead of the logit of pi. And this table might look familiar. It's the same one that Chris showed with respect to the logits. Now we're showing it with respect to the logs. So for a 4-level categorical variable, we have 3 different indicator variables. And those indicator variables indicate x2, x3, and x4. And that results in the following log means when you work out the regression function. And from this, it becomes very apparent that beta 0 is the log mean for level 1, and that each of these beta i's here is just the difference in log mean between that level and beta 1, and the first level. These parameters are sometimes called the effect of level I. So beta 2 is the effect of level 2. It's the difference in the log mean between level 2 and level 1. Now, we express that as a difference with respect to the log mean, and because it's a difference in the log mean, that means that it's actually expressed as a ratio in the original means. So the ratio of the means is the exponentiated parameter from the exponentiated effect parameter. Those ratios are always against the first group. So if you want to make a ratio out of any 2 groups, you simply have to subtract their parameters and exponentiate that. That comes from the fact that the log difference between 2 groups is just going to result in the difference of the effect parameters between those 2 groups. Inference, as before, comes through the same methods that we've seen before. The typical thing that one might want to do is test equality of all of the means. And if you want to do that, that's equivalent to asking whether all of the extra effect parameters are equal to 0. Because if that's the case, as we see here, if all of these parameters are equal to 0, then all of the means are equal. So we will be able to conduct a likelihood ratio test to compare the log likelihoods for the full fitted model against the log likelihood for the null model, create a likelihood ratio test statistic, and compare that to chi-square with I-1 degrees of freedom. That's the number of additional parameters that there are in the full model compared to the reduced or null model. We can make confidence intervals for individual means, since an individual mean is simply the sum of the intercept plus the effect parameter for that particular level. We can make a confidence interval just by adding those 2 parameters together and exponentiating them. That gives us an estimated value for the mean, and so we can make a confidence interval for this whole quantity using likelihood ratio or Wald methods. We can make a confidence interval for differences, or for ratios of means. So a confidence interval for a ratio of the means is going to come from the fact that you express the ratio of means as a difference between these 2 parameters. exponentiate it, and you can find a confidence interval for the difference between the two parameters and exponentiate the endpoints of the confidence intervals. We go through all of that in some detail in a separate program that I'm not going to show here, because there are a lot of other things that I want to be able to get to with you. In particular, what if you have two categorical variables? Chris earlier said that he has a favorite contingency table, but that favorite contingency table has only 2 rows and 2 columns. And he didn't really get into what to do about contingency tables when you have more than 2 rows and more than 2 columns. And it's funny that we're already well into the second half of a presentation on categorical data, and we're finally starting to see contingency tables. And that's because that we find that although it's a little bit more complicated, anything you want to do with a contingency table you can do within the context of a log linear model. So we're going to present this in both the original context of a testing approach and the modeling approach through log linear models. So now we have 2 explanatory variables. I have to first explain that I've been living in Canada now for 11 years, and I've been working very hard at trying to say things that Canadians say rather than things that Americans say. So this letter here has become Z to me, and if I slip back and forth between Z and Z, I apologize. But please try to translate Z and Z as being equivalent to the same little zigzag symbol there. So we have 2 categorical variables, x with I levels and z with j levels. And at each combination of x and z, we observe a count, and that's what this contingency table is. So this is the count of the first level of x and the first level of z. This is the count of the second level of x and the jth level of z. And these counts here are what are called the marginal counts, and they represent the totals. If I draw another line there, they represent the totals across the row or the totals down the column. And so we put a plus in to represent adding across all the levels of that subscript. So the typical interests of a contingency table are twofold. First of all, we often want to find out whether the 2 explanatory variables, the 2 variables, are independent of each other. What does independent mean? Independent is a funny word. It has a technical definition which says that the conditional distribution of one of the variables is the same for each level of the other variable and vice versa. And while that's a fine definition, it's sometimes hard to picture in practice. It's a lot easier to think about it in this context, and that is to say that you expect that the counts that you get are going to follow in the same proportions across each row or down each column. So, for example, you might expect to see, if you have counts in a 10 to 20 to 40 proportion, so this is a 1 to 2 to 4 ratio, then the counts in any other row should also be in something like a 1 to 2 to 4 ratio, approximately. If that's true, then you'll have independence between the row and column variables. And notice that independence, by looking at it going across the rows, is the same as looking at it going down the columns, because in each case we're going to have a 2 to 1 ratio from the top to the bottom row. Sometimes equally important, though, is not just to say whether or not the 2 variables appear to be independent, but to be able to describe the nature of the association. And that's one of the drawbacks of the testing approach to contingency table analysis. You don't really get a good understanding of the nature of the association. So we're gonna do both of these approaches. Both of them can begin from the assumption that the counts that you get in the contingency table, the ith row and the jth column, each comes from a separate Poisson distribution. So this table has a separate Poisson distribution for each of these counts. You can start from that assumption, and that will allow you to derive all of the theory for either one of these 2 methods. So first, we'll start with the testing approach. The null hypothesis that we'll start from is that the 2 variables are independent of each other, and the alternative hypothesis is simply that they're not independent. We're not expressing any way in which they might be dependent. We're just saying they're not independent. So under independence, we can calculate that the expected cell count, if in fact they are independent, then you expect the cell count in any cell to be approximately equal to the product of the 2 marginal counts from that respective row and column divided by n, divided by the total sample size. And so we can compute test statistics, the very familiar Pearson statistic. Chris referred earlier to the fact that, the HIV vaccine paper presented Pearson statistic to show that the vaccine worked. We'll actually see that test in a few minutes. You could also compute a likelihood ratio test statistic, which has that form. You can calculate it by hand if you want to. It's not that difficult to do, neither one of them. Under independence, both of these statistics will have large sample chi-squared distributions with I-1 times J-1 degrees of freedom. That is, they have the number of degrees of freedom equal to the rows -1 times the columns -1. And in both cases, extreme values of the test statistic indicate evidence against the null hypothesis. So large values of the Pearson or likelihood ratio statistic indicate evidence against the null. We tend to prefer the Pearson statistic because it tends to perform a little bit better than the likelihood ratio in smaller samples. So we most often, if we're just doing a test for a contingency table, we'll just focus on using the Pearson. I don't really bother using the likelihood ratio test. So here's the example. This is back to the same data that Chris looked at before and you've seen before. This is the HIV vaccine data, and these were the counts that we had. And now what I'm doing is, Chris has already done this before, I'm creating this contingency table out of them. So we have the two rows, vaccine and placebo, and in the vaccine row we have the count of people who did or did not get HIV, and the same in the placebo row. Now I've covered it up part way, so I'll get rid of that. Now we're going to do the Pearson test. The simple way to do a Pearson test is through the function chi-square.test. And chi-square.test, chi-square test, just takes this table, this array here, just takes this table and plug it in. There is a correction factor that can be used. We don't generally recommend it. There's a correction factor that can be used for small samples to help the statistic act like it has more of a chi-square distribution. But if your samples are really small, you probably should be using a different approach anyway, rather than trying to use something that expects large samples. And once you've run the chi-square test and print out the result, it gives you this. We find the x-squared statistic is 4.2. The p-value is 0.038. And so if you're using a 0.05 significance level, we would declare that there is a significant result here. That is that the two variables, response and treatment, are not independent of each other. They do not have the same distributions, or, in other words, the probability of HIV within the vaccine row is not the same as the probability of HIV within the placebo row. And that's exactly the conclusion that Chris came to earlier when he was looking at confidence intervals for odds ratios. Oh, and just as an aside, by pulling out the expected element of the ind test object, you can just, if you care to, you can print out the expected values. One doesn't have to do that. Yes?
Could you also use the Fisher's exact?
Yes, that's an example of something you could do that rather than doing this correction, that's an example of something that you could do. We don't cover it in the context of a log linear model, but there is a section in the book on exact tests. The chi-square test function doesn't give you the likelihood ratio test. If for some reason you insist on seeing the likelihood ratio test, there's a package called VCD that can give you a function called associatstats, and if you plug your table into associatstats, then you can get the likelihood ratio test and the Pearson test both. In this case, there's a very large sample, and the two test statistics become equivalent in very large samples, and we see that happening here. We have a pretty large sample, and the two test statistics are nearly identical. The p-values are the same down to the second and a half decimal place, and both of them give you basically the same result. Yes. Yes, it can. I'll go over it. The difficulty, though, is that it's a lot easier to see and demonstrate in small problems. This is always the issue in teaching. Do you show things that are easy to demonstrate, or do you show things that are realistic? The two things are often not the same. We've chosen to show things that are easy to demonstrate, hoping that by abstraction one can figure out how to use them in realistic cases. Yeah, you can't do both in the limited time period that we've got. The Poisson regression approach to the same problem. So if you want to do the same problem in the context of a Poisson regression, which will then give you greater flexibility to do some additional things, starts from treating the rows and columns as having indicator variables. So I have indicator variables for my row. I have indicator variables for my column random variable. And then I just put them together in a log linear model the same way Chris did. How many times have I said that now? The same way Chris did, the same way we did in logistic regression. So I have a model for the log of the mean that has this intercept plus the terms representing the x variable. So these are the indicators times their coefficients for the x variable, for the row variable, plus the same sequence of terms for the column variable. This gets to be really a pain to write out, especially when you have perhaps later more than two variables. So there's an abbreviated notation for this, and the abbreviated notation just looks like this, where you take the log of the mean in the ijth cell, and you say that that's equal to an intercept plus, because each of these is an indicator variable, you pull off at most one of these betas for every row. You pull off at most one of these betas for every row, and at one of the beta x's, and at most one of these beta z's for every column. So you just say, I'm going to pull off the xth beta x and the jth beta z, and combine them together into one model. It's an abbreviated way to write the entire model in just 3 symbols instead of, well, however many that is. And it's implicit in this that the two betas that were left off of here, beta 1 and beta 1x and beta 1z, are both 0. They're just not there in the model, so we can just call them 0. This thing is often referred to as the log linear model for contingency tables. Now, having done this, I've got the set of parameters for x and the set of parameters for z. Having done this, it can be shown that this model actually represents the cell counts under independence. That is, the main effects in the log linear model cause the marginal totals to be modeled perfectly. The main effects basically allow these things here to match exactly the same numbers from your original table. But the counts in the interior will end up being these instead of the actual counts. So it doesn't match the counts in the interior, but it does match the counts around the margin of the table. So the beta xi's allow the marginal totals in the table to vary across rows, and they match the row totals perfectly. And the beta zj's allow the marginal totals to vary across columns and match them perfectly. There's no parameters that allow the individual cell counts to deviate from the patterns suggested by the row and column marginals. So what you need to do is you need to add an interaction term to the model. An interaction term is just a coefficient multiplied by the cross product of the two variables. So you have an indicator variable for the ith row of x, an indicator variable for the jth row of z, and then you have a parameter that we're going to use, just call it beta xz, for the ijth combination. And the augmented model can be written, rather than writing out a whole long sequence of explanatory variables, we'll just add that symbol in, which says that when you're in the ith row and the jth column, then you're going to pull off an additional value that gets added into the model. That's the parameter corresponding to the product xi and zj. This turns out to be a saturated model because there are exactly as many parameters as there are counts to be modeled. If you count them all up, they add up to exactly I times j parameters, and there are I times j counts. So you're going to match every count in the table perfectly. So the saturated model can be used to test for independence in the following way. First of all, notice that the null hypothesis of independence implies the smaller reduced model. And in fact, the null hypothesis of independence comes from taking all of these beta xz ij's equal to 0, because remember, the independence model didn't have those terms in it. The saturated model does. So we can make the independence model just by setting all of those parameters equal to 0. So I can fit each model, I can compute the residual deviances and take the difference between them, and that's my likelihood ratio test statistic. Compare that again to the chi-square distribution with I-1, j-1 degrees of freedom, and the reason for that is that there are a total of I-1, j-1 different ones of those additional parameters. And that all can be done in R using either the little a or the big A ANOVA function. This is exactly the same as the likelihood ratio statistic you'd compute on the contingency table. In addition to testing, though, what we can do with the model is we can actually measure the association, which is harder to do in the context of the testing approach. So in a contingency table, we'll once again use odds ratios to describe the association. And Chris showed earlier when he described odds ratios for a 2x2 table that you can write the odds ratios in terms of the expected counts. You can write the odds ratios as this form here, where you take the product of the diagonal elements divided by the product of the off-diagonal elements. So if you have a 2x2 table, you can write the odds ratio very easily. In a larger table, what you can do is you can pick any two rows and any two columns and then collapse that into a 2x2 table. And now that you've got a 2x2 table, you can compute the odds ratio to compare how the odds of these two items change depending upon whether you're in this row or that row. And you can do this throughout the entire table if you wish, and identify the places where there is where there are odds ratios that are not necessarily very close to 1. Yeah, I hate all this notation with the little primes and everything, but it just means that you can pick any two rows and any two columns, and you do the same thing to them, whichever ones you choose. So the odds ratios are easily computed from the log linear model. So you start from taking the log of the odds ratio. And when you take the log of this quantity right here, or this quantity right here, when you take the log of that, then you end up taking the log, you add together the log of the two numerator elements, and you subtract from that the log of the two denominator elements. And then a very nice thing happens. Because each of these logs is now a linear model with these parameters, a whole lot of subtraction takes place, and almost all of the terms wipe out. And the only terms that remain are the interaction terms in the model. So what happens is then if you fit a model that has no interaction terms in it, then all of the odds ratios are equal to 1. All of the terms in the model wipe out when you do that little piece of algebra. If you have interaction terms in the model, then the odds ratio between any two rows and any two columns is simply the sum of the exponentiated sum of the interaction terms for the two numerator values minus the interaction terms for the two denominator values. So you just have to figure out which 4 cells you're working from, and you're going to put a plus and a plus on those two, and a minus on those two in this term here. And you pull off the interaction terms, plug them into that, and exponentiate it, and that gives you the odds ratio from the model. To get the parameter, to get the estimated version, you just plug in the parameter estimates, and then because we're working in a GLM function with estimated parameters, you can get likelihood confidence intervals for combinations of those parameters using the MC profile function. So here's back to the HIV data. If we want to fit this as a model, rather than having it in table form, we have to have it as a data frame. So we're taking our previous table and we're converting it into a data frame. as follows. And now we have three variables within our data frame: treatment, response, and freak. And we have exactly what you'd expect the data to look like. We have our 2 levels of treatment, our 2 levels of response, and the corresponding counts for each one. Now I can fit a model using GLM and a Poisson by saying I want frequency to be modeled as a function of, you saw this notation earlier, treatment star response. This gives us back treatment plus response plus the interaction. And it's the interaction term that we're going to be interested in because that's where the associations come from. When we fit this, you may remember I said that this was a saturated model. It gives us back a deviance, a residual deviance, which is a number that's trying to be 0. That's telling us that we've basically fit all of the counts perfectly. We have nothing left. It's sort of like getting a sum of squares of 0 in a regression. You've fit every count, you've fit every observation perfectly. The coefficients come out, so rather than showing you the whole output, which gets rather long, the coefficients come out here in this segment. And so we have we have an indicator for placebo because placebo is the second level of treatment. We have an indicator for a coefficient for no HIV because no HIV is the second level of response. And then we have an interaction term for the combination of placebo and no HIV. So the indicator variables in each case were set up to ignore the first alphabetical level, so it's ignoring the vaccine and the HIV level and using the second levels to set their values. So this results in an estimated Poisson regression model under dependence, so not assuming independence, because I have this interaction term here. An odds ratio that I would compute, so if I were to make my 2x2 table look like this, with the order in which things sat were, oops, it wasn't the first alphabetical level, it was just the order in which they were entered into the table. Vaccine, placebo, HIV, no HIV. If I want to make an odds ratio out of that, first of all, I can simply do the calculation, but if I do the calculation, I have to decide what order am I pulling in these counts from. So I need to get my odds ratio to be beta 1, 1, so I need, this is the 1, 1, 1, 2, 2, 1, 2, 2. I need to take the product of these two, or the sum of those two, subtract off the sum of those two, and that's what this does. Exponentiate that, and when I realize that this one, and this one are all 0, they don't show up in the model. The only one that shows up is the second one for placebo and no HIV. That's minus 0.38. So I exponentiate minus 0.38, and that gives me back the number 0.68, and then we're left to figure out which one of those 8 interpretations of an odds ratio that 0.68 represents. And the way to go about that systematically is to look at the table that you've just created. So we have just created a table that looks at the odds of no HIV for someone on placebo, because those things were what the parameter were made from. The odds of no HIV for someone on placebo are 0.68 times as high as the odds of no HIV for someone who is vaccinated. No HIV on placebo are 0.68 times as high as no HIV for someone who is vaccinated. We can flip that around and say the odds of HIV for someone who is vaccinated are 0.68 times the odds of HIV for someone on placebo, which is suggesting that the vaccine is working. You can also get confidence intervals. Chris has already shown how to get confidence intervals for parameters from a GLM object, so I haven't done that here, but they are shown in the program. The test for independence, the test to see whether there is any treatment by response interaction, can be done using the ANOVA function on the model, and that gives a test for these two variables, but the real test that we want is the test for the interaction, and that gives us a p-value of 0.38. It's exactly the same test that we saw before when we did the associates function. So there appears to be some evidence that the HIV vaccine is giving people less of a chance of HIV than they would get otherwise. Okay, before I move on, any questions? Okay. There are lots of ways to extend this, just as there are lots of ways to extend the logistic model. So the first extension is, what if you have more than two explanatory variables, which is very often, you frequently will have more than two explanatory variables. This HIV vaccine could have been given, for example, to people of either sex, or if you wanted to expand that further and think in non-binary terms, there could have been a lot of different levels of gender. There could have been additional variables that one might have measured, whether one was in a monogamous relationship, whether one was this, that, or the other. So you could have had a number of other variables, categorical variables associated with this same thing, with this same problem. And so you could have a multi-dimensional table if you had the interest in doing that. So you could conceivably have, say, p categorical variables, and if you did, that would form a p-way table. So a three-way table just makes the same thing multiple times over a third variable. We call this W, I believe. So W has levels 1, 2, 3, and 4, and you just make the same table multiple times, except now counting the counts that correspond to the different levels of W as they fit X and Z. And then you have questions that you might ask about this table. So, for example, which pairs are associated and which are not? Are X and Z independent of each other? Are X and W independent of each other? Are Z and W independent of each other? Are the associations between two variables consistent across levels of the other variable? So suppose there is an XZ interaction. Suppose X and Z are not independent. Suppose they are dependent. They're associated. Is the level, or is the amount of the XZ interaction the same for all four of these tables, for all four levels of W? You can ask questions like that. They become interesting. So that would be, for example, if the vaccine is going to be effective against HIV, is it equally effective for people in all different types of relationship? Or is there an interaction there? Does the effectiveness change depending upon the type of a relationship a person is in? Or does it change depending upon their sex? The parameters in the models will include the main effects, which do exactly what we saw them do before. They simply adjust the marginal totals so that they match the marginal totals of the table, of the full table. You'll have one set for each variable, so you'll have beta I x's, beta z j's, beta w k's, and one set of those for every different variable. You'll have two-way interactions that allow the associations to have odds ratios other than 1, and you can have them between any sets of variables you wish to have. You don't have to put all pairs in the model if you don't believe all pairs are important. But then that's an assumption you're making about the model. Just like in any regression, you don't have to put variables in the model if you don't want to, but you run the risk of missing something. So you have a pair of variables, xz. You could have the xw and the zw interactions also added into the model. Not including an interaction term forces all of the odds ratios relating to those two variables to be equal to 1. So if you want to allow them to not be 1, you have to include the variables in the model. But then there's this new concept. A three-way interaction will allow two-way associations to change across levels of the third variable. That's what I was saying before. Is the HIV protection from vaccine going to be the same for all levels of sex or for all levels of a relationship? Whenever you put three-way interactions in the model, you also need to include sets of parameters for all two-way interactions involved in that three-way. So if you have a WXZ, then you want WX, WZ, and XZ all to be in the model. We have an example of this in our program, Paul Ideal Nominal. It gets large. I could spend the rest of our time going through that example. So rather than do half of a job of it, I'm leaving it to the example in the program. Similarly, one can consider ordinal categorical variables. So Chris has already showed you how to model ordinal categorical variables in the context of a multinomial model. You can have a contingency table with ordered categorical variables. For example, the example that we have in the political ideology problem has people self-identifying their belief in the political spectrum from very conservative, somewhat conservative, moderate, somewhat liberal, and very liberal. And I think if you think about those categories for a moment, you realize they're ordered. They're ordered with respect to very liberal is closer to somewhat liberal than it is to very conservative. There's clearly an ordering among them. The way you treat ordinal categorical variables in a log linear model is simply to assign scores to them and treat them as numerical. I mean, it sounds like cheating, but that's exactly what is done. You assign scores to the levels. So in the political ideology example, you could assign the scores 1, 2, 3, 4, 5 to the 5 levels and go with that. But if you thought that there were different relationships among the scores, if you thought, for example, that being very conservative or very liberal is farther away from the middle than slightly conservative and slightly liberal are to the middle, then you could go with something like 0, 2, 3, 4, 6, and leave gaps in to indicate that categories are farther apart in some sense. The whole philosophy of that becomes somewhat cumbersome. And it's always a good idea, if you're not really sure what scores to use, to try several sets and make sure your conclusions don't change drastically. If there's an additional nominal categorical variable with j levels, then you can start from the independence model, but then you want to model the association as a function of the scores. So you create, basically, it's like creating a different slope on the ordinal variable for each level of the row. The main effect of each variable is left nominal, but the different slopes on the ordinal variables are put in for each level of the nominal variable. And what that does is it creates a particular form to the association. If you work out the log odds ratio the way I showed you before, and you plug in all the parameters of the model, it turns out that it has this form, and this form has a nice interpretation. It says that the log of the mean ratios changes linearly with the difference between the category scores. So that means, for example, in my political ideology example, that ratio there, the log of that ratio, compared to the log of that ratio, if these scores are 1, 2, 3, 4, and 5, if I compare the log of that ratio to the log of that ratio, it's the same as the log of that ratio to the log of that ratio, because all of those cases are 1 unit apart. And furthermore, the log of the ratio between 1 and 2 is half the size of the log of the ratio between 1 and 3, because those are 2 units apart. So you're just putting a model on how the log ratios are going to change across the levels of the ordinal variables. And so there is an example in the political ideology ordinal R program. Okay, what if the counts are based on different amounts of sampling effort? This is a completely different question from what we've looked at before, or it's a completely different twist from what we've looked at before. So when I gave examples before, I said you're going to count the number of cars per hour. But what if some days you're out for 20 minutes and other days you're out for 3 hours? I have a friend who does mist netting of birds in the rainforest of Ecuador. And some days her sampling is cut off because they run into a storm or something. So they only sample for a certain amount of time. She measures the amount of time they spent, and they capture different numbers of birds. As you might imagine, if you sample for 3 hours, you're more likely to capture more birds than if you sample for 20 minutes. But you're not really trying to measure the effect of how long you sample. That's not the point. The point is to understand the effect of other factors that may be present. So, for example, cars over a bridge will increase with the amount of time watching. The count of auto accidents increases with miles driven. The count of weeds increases if you increase the size of the plots. This sampling effort is something generically called exposure. So if you give yourself more exposure to a process, your counts will increase. That only makes sense, but that's not really the point of any modeling problem. All analyses thus far have assumed that the mean counts had common exposure. But what if they don't? So in other words, by having common exposure, the means vary only by changes in the intensity or the rate at which events accumulate. That's a way to think about this, is that by watching over a bridge, cars accumulate into a count. If you give yourself longer time, cars are accumulating maybe at the same rate, but they're accumulating at over a larger period. So you could have, if you sampled from midnight to 6 a.m., you could have more cars crossing the bridge than you do between 7:30 and 8 a.m., when in fact the intensity is much higher at the second time than it is at the first time. So because exposures are different, and you accumulate counts at a rate r over exposure t, a count is just the rate times the exposure, right? It's cars per hour times the number of hours is the number of cars. And if cars change because of changing exposure, that interferes with your comparison of the rates. If you want to know what factors affect the intensity with which the counts are accumulated, the differences in exposure interfere with that. So you want to model the rates as the count divided by the exposure. What you're really interested in is the cars per unit time, or the weeds per unit area. You're not interested in just the raw count of the weeds or the raw count of the times. So we can fit all that in the context of a log linear model simply by modeling the rate as a function of all the variables that you're interested in seeing. So how do these variables affect the intensity with which these counts accumulate? How do they affect the rate with which these counts accumulate? But because of the fact that this rate is equal to the quotient of the mean count divided by the time, then we can fit this as a Poisson model for the mean count by taking the log of mu minus the log of t. This rate is the log of mu minus the log of t. We just move the log of t over to the other side of the equation, and we say that the log of the mean is equal to the log of the exposure plus the linear model. Now that log of the exposure isn't a variable per se. It's just a quantity. It's called an offset. There's no parameter on it. It's just an adjustment factor whose value you know in advance because you know how many hours were spent sampling. You know how much exposure there was for each observation you've taken. It's just an adjustment to the model that sets off the model for different individuals with different amounts of sampling. And the parameters then, because of the fact that we've written the model originally in this form, the parameters relate to the log rates rather than the log means, which is what you want. You're trying to model the differences in intensity, not the differences in raw counts. So the parameters do tell you about those differences in the rates, in the log rates rather than the log means. As an example of this, it turns out it's the same. I looked it up, by the way. The person who did the tomato spotted wilt virus, he did come to me in advance, and he knew that he was going to have 16 greenhouses. And he had ideas about which treatments were more important, and we assigned them to greenhouses in a certain systematic way. Also, there were some other factors involved in the greenhouses that involved the locations of the greenhouses. So we assigned these treatments to the greenhouses in a systematic way. The fact that there were 6 treatments and 16 greenhouses means that there was unequal replication. The same person, he was a friend of mine in Manhattan. We went to lunch a lot, and we talked a lot about insects. We had disgusting lunches. He did another experiment involving beetle egg evolutionary responses to crowding in beetles. So the question was, the certain kind of beetle that feeds on a certain kind of plant, when there are lots of other beetles around, do the females adjust their egg-laying pattern to lay fewer eggs so that there's not too much competition for the plant that's available? And when there are fewer females around, do they lay more eggs? Okay? I mean, you can kind of picture, okay, this is a question you could ask if you like studying insects. I always told him that he's lucky his problems are so small. So he did an experiment to see how crowding and temperature affects eggs laid per female of a certain kind of beetle. Notice that the question he's asking is explicitly a rate question, eggs per female. And the way you get crowding is by making these little boxes, these little plastic boxes, and putting a female in, or putting 5 females in the same amount of constrained area. So he had either 1 or 5 females in, and then these boxes were held in temperature chambers at either 21 or 24 degrees, and then he would count the eggs over a prescribed period of time. But the problem is that the females didn't kindly sort of mark their eggs so that he knew that female 1 laid these eggs and female 2 laid those eggs. He just said there's this many eggs in this box with 5 females and there's that many eggs in this box with 1 female. Clearly this is an exposure problem, right? You have 5 females on the one hand, 1 female on the other hand. So you have to account for the different exposure in regard to the number of eggs that end up being laid. So we fit a Poisson rate regression model. So we have treatment is the boxes with 1 or 5 females. We have the temperature, which is the temperature of the chamber. This is the count of the number of eggs, and the different exposures we count as the variable females. And in GLM, you can run the Poisson rate regression or the Poisson regression with offsets just by ignoring the offset in the formula statement. So in the formula statement, you simply say that the number of eggs is going to be a function of the combination of treatment and temperature and the interaction. But then there's an additional argument that goes into GLM, and that's the offset argument. And you just say offset equals the log of whatever your exposure variable was. In this case, the exposure variable is recorded under the variable named females. And then the parameters relate to testing and tests relate to comparing the rates, the eggs per females, across the different treatments and across the different temperatures. So because we don't have enough time to go into the details of that, I don't have the program to show you here, but it's all in the program beetleeggcrowding.r on the website. So you can go home and run that and see what happened to those girls. And that leaves us, when are we scheduled for the break? 3:15? 3:15, okay, so we can move on now. For the most part, we've finished talking about the 3 main kinds of models that are used in categorical data. The binomial model, the multinomial model, and the Poisson model, and we've given a few extensions of them. Now we're going to talk about some things that apply essentially to all different kinds of models, and that is model selection and model evaluation. Model selection has 2 parts. Model selection means selecting a probability model that's appropriate, and we've already done that. Do you have counts that come from trials? Well, then let's use a binomial model, maybe with a logistic form. Do you have counts that are unrestricted? Do you have counts that have an exposure attached to them? So you select the appropriate probability model. That's part 1, and most of the time there's not a lot of comparison or statistical work that needs to be done to select the right probability model. Sometimes there is, and I'll get into an example of that in a little while. The second part of model selection is identifying an appropriate set of explanatory variables, because researchers often measure more things than what they really need. There are a lot more variables in a problem than what actually need to be in the problem. It's better to have more than what you need than to leave something off. And in particular, these days, with the ability to measure, entire genomes and massive amounts of information about individuals on the internet, you're going to have huge numbers of variables, and they're likely not all going to be important. So that model selection involving selecting the appropriate set of variables is very important. So the first thing we'll do is we'll present methods to select an appropriate set of explanatory variables from among a larger pool of variables. And we'll focus on information criteria rather than hypothesis tests, although there are some other methods of variable selection, and I'll touch on a few of those. Once the variables are in the model and they're fully specified, we need to check model assumptions. So we need to do things like residual diagnostics and look at goodness of fit statistics for the model. And then finally, we'll explore a common model assumption violation called overdispersion that happens all the time with categorical data, and I'll offer some solutions. So first, variable selection. Variable selection means reducing the number of explanatory variables that get used in a model. That's all. Why do we want to do that? Well, for one reason, sometimes the number of variables you've selected is larger than the number of observations, and you actually can't fit your model. So you have to do something to get rid of some of the variables. But even if that's not the case, complex models are harder to understand. It's a lot better to explain a model if there are only 2 variables than if there are 27 variables. But even if you don't care about explaining it, there's a statistical reason to want to do variable selection, and that's something called the bias-variance trade-off. And if you don't understand anything about variable selection, this is the thing you need to learn, is the bias-variance trade-off. The bias-variance trade-off comes from the following features. Number 1, models that are too small may predict poorly because they're missing important features. So picture trying to be real parsimonious about modeling field goals and saying, okay, well, I'll just get rid of the distance variable. You're not going to have a good model. We've already seen that distance variable seems to be very important. So you don't want to get rid of variables that are important. So that might suggest, well, let's just keep as many variables as we can. But the problem there is that every time you have a variable in the model, you have to estimate a parameter, and estimating a parameter adds variability into the prediction process. Every parameter you estimate creates variability in your predictions. Picture of a model in which that's completely flat, that has no variables. Or picture a truth that has no variables in it, a completely flat mean. But you add a bunch of variables to it. Then you're going to have predictions that are all over the place around the mean rather than a nice flat prediction. So you've created variability in this. So what you need to do is find a place where you can compromise between making sure you have the important variables but not having too much variability in your model and your predictions. This is where information criteria are nice. Historically, as in many years ago, all variable selection was done by hypothesis tests. But we don't need to do that. Information criteria are much cleaner for doing model comparisons. Information criteria are measures based on the log likelihood that include a penalty for each parameter estimated in the model. So the idea is, just like with linear regression, you may be familiar with the notion that in a linear regression, the more variables you add, the smaller your residual sum of squares becomes. It doesn't matter if they're important variables. If you add another variable, you reduce your error sum of squares. You add another variable, you reduce your error sum of squares. It's the same with likelihoods. If you add another variable to a model, your likelihood increases. Whether it increases meaningfully or not is another question, but it does increase. So adding variables to a model improves the likelihood, but also increases the penalty. So you put a penalty on the likelihood, and it looks something like this. So that adding a variable can result in either a better or a worse value of the criterion. It looks something like this. There are two terms to an information criterion. The first term is just -2 times the log likelihood. So the higher the log likelihood, the smaller that value. For some reason, it's all written in terms of negative signs. So you want a really, really small value of -2 log likelihood. But if you start making it small by adding useless variables, the second term kicks in, which is a penalty coefficient times the number of parameters in the model. So if k is some number and you start increasing r, then you're adding to this value while you're taking away from it by increasing the log likelihood. So the balance between having a small value of -2 log likelihood and not too large a value of the penalty is where you want to find a good model. As a result, small values of this criterion are better because they have a high log likelihood with a small number of parameters. That's the best model you can find. The three most common criteria are Akaiki's information, the corrected Akaiki information, and the Bayesian information criterion. And they all differ only in what penalty they choose to put on the parameters. The penalties are 2 for the AIC, 2, and I'll separate this out there. Notice that there's that 2 there, and then there's this n over n minus r minus 1. So what that does is it inflates the 2 corresponding to how much of n you're consuming with parameters. If you have a large number of parameters relative to your sample size, then this number starts to blow up. It wants to keep you from throwing in too many parameters to approach a saturated model. And BIC uses the log of the sample size as its penalty. So the log of the sample size for most sample size and parameter combinations, that's usually the largest penalty of the three. So BIC will put the largest penalty on adding variables, which means it's going to prefer the smallest model of the three. AIC is the smallest penalty, and it's going to let you have the largest model of the three. So the way you use information criteria in the traditional approach, which I will try to improve upon in a little bit, is you first fit a set of models. So you have to have a set of models to select from initially. Somehow or another, you have a set of models you're interested in. You fit a set of models. You choose your parameter. You choose your penalty coefficient. You fit the models, and you compute the information criterion on each model, and then select the model with the smallest information criterion. I mean, if small is good, then that would seem to be a way to do it. And it doesn't require that your models are nested the way hypothesis tests do. So you can compare models that have any combinations of parameters in them and still be able to perform the comparison and make a selection among them. The question, though, is which models should you compare? And suppose we have a pool of capital P explanatory variables. And I don't know what these variables are, and I don't care. They might include transformations if you were interested in transformations. They might include interactions if you wanted to have interactions in there. So there's just this pool of variables that you have to choose from, this capital P. Pretty much everybody will tell you that the thing that you should do is use expert-selected models where possible. Somebody who knows something about the problem should tell you what models ought to be interesting. And we can all sit here and we can all say, yeah, that sounds right, yeah. And then as soon as somebody comes into your office and says, I need to know which variables are important, and you turn around and you say, well, I need you to tell me which models you think are useful. Which models do you think are the most important ones? They're going to say, well, if I knew that, I wouldn't be here. So an awful lot of the time, researchers want statistics to tell them which variables are important because they're not sure. And so it ends up being left to some automated procedure to try to put some measure on the importance of the variables. So otherwise, we have to find some algorithm and use the algorithm to fit the models and select them and to compare them. A lot of different algorithms exist for doing this, and if you walk around the meetings, you probably will have discovered 73 more of them, because they're all over the place. There are new ones being developed all the time. One of the classic ones, classic as in it's been around since, oh gosh, before the 1960s even, is all subsets regression. And that is using the most brute force thing you could imagine. Literally make every possible model you can out of your set of variables, fit every single one of them, slap an information criterion on each one, and find the best. That is a massive search, at least if your number of variables is large. I mean, really, you can't do it for more than, depending upon the complexity of your problem, you can't do it for more than maybe 30 variables, 35. I've seen a program that, I've seen an R function that will do it for 50, but you better not have too large a sample size. That's a lot of models it has to consider. So let's get into an example and see how this works. We're going to use a function called glmulti from the same package glmulti to perform all subsets regression for you on the place kicking data. So Chris has showed you this data before. The glmulti function has a couple of arguments in it. The method equals h does all subsets. I don't know why they call it h. Exhaustive. Yeah, I think it's exhaustive. That is what it is for exhaustive, but somehow or another it's h. Maybe it's a different word in the language of the package author. Level equals 1 does main effects. Level equals 2 will include interactions for you, but notice that those interactions count toward your pool. So if you have a lot of variables and you try level equals 2, you're already sunk. Level equals 1 will be about as much as you can do, even if you can do that. The package is described in much more detail in a paper by Calcagno and de Mazencourt. Here's the data. We're reading in the data once again, and now we have all of these variables. This is our response variable, good, and we're going to put all of these variables into a model. There are 8 variables. 2 to the 8 is only 256. We only have to fit 256 models. Chris can do that by hand while we're waiting. And we're going to fit every possible model, and we're going to put an information criterion on it and measure how good the models are. I'm not going to say anything about that other than that it's there, and I hate the fact that it's there. So we'll run the glmulti function. glmulti has a formula basis, and there's this. I kind of scribbled over a bunch of stuff there, didn't I? glmulti can work with a formula, and there's this little thing that I don't think Chris has showed you yet. This little dot means everything else. So if you have a bunch of variables in a data frame and you pick one of them out and call it y, and you say tilde dot, it'll take everything else and stick it in on the right-hand side. Yes, that's a lot nicer than saying x1 plus x2 plus x3, assuming you even called your variables simple things like x1 plus x2 plus x3. So that's a big time saver right there. I actually like to set this to true because it will run a series of plots that it will update periodically for me as it's running through the models. But when we run it in the slides, it blows up the slides. So we had to set it to false. I like setting it to true. And this report equals false could also be set to true if you want to see what's happening as it's working. I'm telling it family equal binomial, link equals logit, because we're fitting a logistic regression model. I'm only asking for main effects. I'm not asking for interactions. We're going to do an exhaustive search, and for no real reason, I've chosen AICC. I could have chosen BIC. I could have chosen AIC. I've chosen AICC. I don't want this to become one of those Fisher things where he said, well, you know, 1 in 20 seems reasonable. And now the whole world is stuck on 0.05. I chose AICC for no particular reason. So I've run the search. I've created this object called search1 AICC, and when I print out the results, I get a little bit of information from my search. So I had, it kept automatically, it keeps the top 100 models around. Okay, let's be honest. Model number 184, you don't care about. So keeping the top 100 models is more than enough information for you to work from. The best information criterion found was 766. The best model had distance, change, PAT, and wind in it. And then there's this thing called evidence weight, and this thing called, well, the worst AIC in the top 100 models was 780. There were 12 models within 2 AIC units, whatever that means. We'll get to that in a bit. 51 models reached 95% of the evidence weight. We'll get to that in a little bit too. But the main thing is it's picked out our best model for us. It's distance, change, PAT, and wind.
I didn't even explain the distance and change.
Hmm?
You might be able to explain what the PAT window.
Oh.
Sorry.
Okay.
I think I skipped that when I finished.
Well, let's talk about them for a little bit. PAT, Chris mentioned that there were a whole lot of kicks that happened at 20 yards, and that he called them a special kind of kick. They were points after touchdown. So PAT is an indicator variable that indicates whether a kick was a 3-point field goal or a 1-point after touchdown. One of the special things about the 1-point kick is that it's always taken from directly in the middle of the field. If the team chooses to, and they always choose to. They take it from directly in the middle of the field because that maximizes the angle to the goalposts. As soon as you move to a different angle, you change the probability of making the kick by changing the angle of the kick. So PATs are always taken from the middle of the field. You might begin to imagine then that a 20-yard PAT might have an inherently different probability of success than a 20-yard field goal. And so that PAT indicator indicates whether it was a PAT attempt or a field goal attempt. And this wind is also, that's an indicator. At the time, we didn't know which direction the stadiums were in and which direction the teams were kicking into at any given moment. Nowadays, you could get better data and probably know which direction and what the wind was and all of that stuff at the moment of the kick. But all we had was the weather information at the start of the game. So this is an indicator as to whether or not there was at least a 15 mile an hour wind at the start of the game, because after some exploratory analysis, he found that 15 was about a point at which there seemed to be something happening. So that's what those two variables are. What? That's what I said this is. That's fitting only main effects, no interactions. And a quick little summary of the top 5 models. If you ask for weight table, and then I take the resulting object and I do some things to make it look a little nicer. Otherwise, it comes out looking kind of ugly. The weight table shows me that the top 5 models. Well, this is the top model. The next best model includes the variable week in it, which is just a categorical variable saying which week of the season was it. So different weeks, who knows, maybe there's a big weather system covering half the country. Maybe as it gets later in the year, it gets colder and snowier. As it's earlier in the year, it's sunnier and warmer. Maybe this, maybe that, who knows. But does the probability of making your place kicks change as you go throughout the season? This one here continues to have weak, but it seems to have got rid of wind. This one here gets rid of weak and wind. This one here gets rid of change. So you see, all the top models include distance and PAT. All 5 of the best models had distance and PAT. That kind of tells you something. Furthermore, 4 had change, 3 had wind, 2 had weak, and none of them had these other 3 variables, which I won't bother to explain because they're useless. Okay, so ignoring for a moment that we got one top model from looking at it, we also get some information out of the next 4 models, don't we? We learn a little bit of something about our variables. We learn that some of those variables are a little more stable, or a little more consistently important than others. We learn that PAT and distance are always needed, and that some of these variables can float in and out of the model and not really be missed that much. Maybe. It all depends on what some of this information means, and I'll explain that to you shortly. So there are some clear patterns, but there's also some uncertainty. It's not entirely clear whether all of these variables are important or not, because they're not in every single one of the top 5 models. So let's take a 15-minute break now, and I'll finish this off for you when we get back.